Do you guys still remember what a uniform distribution looks like this? So all the frequencies are the same. Symmetric distribution, still remember what a symmetric distribution looks like this. Even a picture will be better than 1,000 words to just see what a symmetric distribution looks like. Graph can be viewed as a bell-shaped curve. Like this, guys. Skewed right. Can anyone remind me what a skewed right distribution is?
Where the bars go down to the right.
Yes. Tail to the right. The distribution has a long tail to the right. And let me ask you here, guys. In a skewed right distribution, is the mean bigger than the median or the median bigger than the mean? Let's see if we still remember that from last Monday. Remember, the mean follows the tail of the distribution.
The median is larger than the mean.
The mean follows the tail of the distribution. It's closer to the tail. So the mean will be right here toward the end. And you know, on the number line, guys, as we go to the right, the numbers get larger. So the mean is larger. Mean is bigger than median. Let's do a skewed left distribution. It will be something like this, guys. Since the mean follows the tail of the distribution, so it's going to be toward the left, so it's going to be smaller. Tail to the left. Mean is less than median. Please remember that. Could have some questions, you know, on this. That's very important. Now, what is the mean? Add up the quantities and divide by the number of quantities. That's the definition. What is the median? It's the value in the middle position. Mode is the value that occurs most often. So that's a summary of what we have done so far. Let me just take you back. These are examples, guys. This is symmetric. This is uniform. This is skewed to the left distribution, and this is skewed to the right distribution. In a symmetric distribution, the mean, the median, the mode are the same. In a uniform distribution, the mean and the median are the same. And the mode is everywhere. Everything repeats the same number of times. So we say there is no mode because every single value repeats the same number of times. We did the measures of variation, the standard deviation, and I'm gonna show you the formula for the standard deviation, guys. Again, you don't need to use it, but let me just remind you what we did last time with the formula of the standard deviation. We did this. So just to remind you of the formula that we did last time, we took a data set. Let's say I'm going to take this data set and try to find the standard deviation. So what we did, guys, we found the mean first, which is X bar. You add them up and divide by 4. This is a 20, and you divide it by 4, it will be 5. And we put 5, 5, 5, 5. We subtracted each value from the mean. This is called the deviation from the mean. There was a 0, there was a -1, there was a -2, and there was a 3. Then we squared deviations. So there was a 0. -1, when you square a negative number, guys, you get a positive number. So -1 times -1 is a positive 1. And when you square a negative, you get positive. So -2 times -2 is a 4, and that's a 9. And then we adding them up. That will be 13 and 1, 14. Then we divide it by the sample size minus 1. I have 1, 2, 3, 4. What's 4 minus 1, guys, is 3. And we're almost done. We use the calculator here to divide 14 by 3. 14 divided by 3, guys, is 4.666. Let's make it 4.67. And then we took the square root. And let me show you guys how to use the calculator to find the square root again. So just put second and look where the square root is, right here, x squared. Why second? Because it's in blue. Anything is a function in blue, you have to press the second key first and then put 4.67. It's 2.16, and that's your standard deviation. So what the formula says, guys, look what the formula says. You find the mean and you subtract, you know, x, the mean from each x. Sum, and then you square each one. That's where the square is. Sum means you add them up. Divide by the sample size minus 1, and then square them. And that's the formula for the standard deviation. Now the formula for the variance, guys, variance is the square of the standard deviation. You just get rid of the square roots. You see, it's the same formula, but without the square root. Now, this is for the sample. For the population, here's the formula. That's why we have two formulas, guys. Let me show you the formula. They're pretty much the same. It's called sigma, square root, sum of x minus. I'll explain what this simple is, over n, not n minus 1. So we don't do n minus 1. Let me tell you what this simple is if I didn't mention that last time. X bar is called the mean from the sample. This one, it's called the mu. This is how you pronounce it, guys. It's the mean from the population. To find the mean, guys, you do the same thing. You add up the quantities and divide by the number of quantities. But if he gives you a sample, when we write the simple for the mean, we do X bar. When he gives you the population, when we write the simple, we write mu, just like that. So just try to get used, you know, to writing this, because this is a population mean. So this is a population mean, and this is sample mean. This is sample standard deviation, and this is a population standard deviation. And the population variance, guys, will be like this. You just get rid of the square root. That's the formula. It's called sigma squared. Again, guys, you don't need to worry about those formulas, but you really need to know where they came from, because you'll be using the calculator to find, you know, the mean and the standard deviation. Okay, and I've been emphasizing a lot about the difference between S and sigma, because from my experience in this class, guys, I give students a data set and tell them this is a sample, and then I ask them to find the standard deviation, and some students will go to the calculator and give me sigma as an answer. That's not correct. When I give you a sample, the S is an answer, not sigma. But when I say this is the population, I give you a data set and say this is the entire population, then sigma would be the correct answer. So as long as you know the difference between the two, guys, that's all I care about. Okay. Any questions, guys? Does everyone feel comfortable, just entering a data set and finding the mean, median, and standard deviation into the calculator? You guys, you think you can do that?
Yeah.
That's good. All right. Let's share this with you. This is the end of section 2.4, and we have one more section, and we'll be done with this chapter. Do you guys agree with me that this is a symmetric distribution? Look, it's bell-shaped. So the mean will be right here. This is the mean of the distribution. In real life, guys, most data sets, when you collect them and draw a histogram, they're going to turn out like this, a bell-shaped curve. He says the mean is 22 here. So actually, my mean is 22. I'm going to put 22 right here. This is a number line, guys. You learned what a standard deviation is and how to find the standard deviation. If you have a data set, any data set, in general, guys, the values in the data set cannot go beyond the 3 standard deviations from the mean. For example, he says the standard deviation here is 3. So I'm gonna scale this number line and add 3 every time on the number line. So if I add 3 here, what do I get, guys? What would that be here? Plus 3, 25, plus 3, 28, and plus 3, 31. Now I want you to subtract 1 standard deviation here. The standard deviation, he gave it to us to be 3. So it will be 22 minus 13, 19. 19 minus 3 is 16, and 16 minus 3 is 13. So it looks to me like the distribution, guys, it starts as low as 13 and goes as high as 31. The data set, your data values, guys, most of them should be between 13 and 31. They don't go usually above 3 standard deviation of the mean. Let me give you another example. Let's say on the first test, guys, I come to you and I tell you your average score on the test was 75. So that's the mean. And the standard deviation was, let's say I tell you the standard deviation was 4. Here is the conclusion that you can make, guys. Add 4 3 times to 75. If you add 4 3 times, 75 plus 4 is 79. Plus 4 is what? 83. And plus 4 is 87. Now subtract 4 3 times from 75. If you subtract 4, will be 71. If you subtract 4, it will be 67. And if you subtract 4, it will be 63. You guys can be very sure, almost 100% sure, that the scores on the test for all students were between 63 and 87. Usually scores do not go beyond the 3 standard deviation. 3 standard deviation is too much. So you can you can have an idea about the performance in the class, thinking that almost everybody scored between 63 and 87. Now, if this standard deviation, guys, was 6, let me show you. Let's add a 6. 75 plus 6 will be 81. 81 plus 6 will be 87. 87 plus 6 will be 93. Now let's subtract 6. 75 minus 6 is 69. 69 minus 6 is 63. And 63 minus 6 is 57. Now, guys, you can make a conclusion that the scores on the test for all students on the exam were between 57 and 93. Did you guys notice that when the standard deviation is large, there is a more widespread of the data? Before it was 63 to 87, and now look, now it's 57 to 93. So there is more widespread of the data when the standard deviation is large. So if I go back to this, guys, this is the mean 22, and I added the 3 standard deviation plus 3 plus 3 plus 3. And here I subtracted 3. And let me tell you, show you, tell you what statisticians have found out about data sets that are bell-shaped. They say, this is from an experiment, guys, 68% of the observations fall within 1 standard deviation of the mean. Do you guys understand what within 1 standard deviation of this mean means? Within could be up or could be down. So 22 plus 3 is 25, and 22 minus 3 is 19. So statisticians notice that 68% of the data is within 1 standard deviation of the mean. So this is 68%. Now, they also notice 95% of the data fall within 2 standard deviation of the mean. 2 standard deviation of the mean. Can someone tell me what the numbers that represent 2 standard deviation within the mean? What would they be?
28 and 31.
Exactly. 28, and you have to go the 2 standard deviation this way, and what? 16. You see, guys, the coverage on the curve now, that's 95%. Now, I told you guys, almost everybody is going to be within 100%, but I didn't say it's exactly 100%. Look at the number. 99.7% of the data will fall within 3 standard deviation of the mean. So if we go from here, guys, watch. Statisticians found out that 99.7% of the observations fall within 3 standard deviation of the mean. Do you guys know where the 0.3% is? Why this is not included? Any idea? What do you think those values are that don't belong there?
Are they outliers?
These are the outliers, exactly. There could be some outliers. Like, I'll give you an example of an outlier. Let's say, guys, I give you a test out of 100. Everybody scores between 90 and 100, and a student score between 0 and 10. Would you guys agree with me that the 0 to 10 doesn't belong there?
Yes.
Just that person is in the wrong class. That score between 0 and 10, let's say it's a 3 out of 100. That's going to be an outlier on the small side. And I'll give you another example. I'll give you a test. Everybody gets a C except for 1 student who get an A+ on the test. That's going to be the 0.3% because it doesn't seem like it belongs there. Maybe that student should go move to the next class. So that's what that's why we don't put 100%, but you guys can be sure it's 99.7% of the data will be within 3 standard deviation of the mean. So what I like you guys, I like you to try to memorize this rule. If the data set is bell-shaped, 68% means 68% of the data fall within 1 standard deviation of the mean. 95% of the data fall within 2 standard deviation of the mean. And here 99.7% fall within 3 standard deviation of the mean. And let me show you how to apply this, guys. Let me ask you some questions here on this data set. Okay, I'm gonna just draw it again to make it look nicer, cleaner. And then I'm gonna ask you a few questions. So this is the mean, guys, 22. And I'm gonna add a 3 each time. 25, 28, 31, and subtract 3. When you go to the right of the number line, guys, you add numbers. When you go to the left, you subtract numbers. So that will be 19, 16, and 13. Okay, now I'm gonna ask you some questions, guys. What percent of the scores fall between 19 and 25? What percent of the scores fall between 19 and 25?
68%.
68%, because that's within one standard deviation of the mean. Now I want to make it harder on you guys. What percent of the scores fall between 22 and 25?
34%.
You guys agree with the 34%? Because within one standard deviation of the mean means one standard deviation above and one standard deviation below. They're split up 34%, 34%. That is correct. That is a 34%. What percent of the scores fall between 16 and 28?
96%.
You mean 95?
95, sorry.
That is correct. 95%. Okay. What percent of the scores are below 22?
It's between 31 and 13.
No, below 22. This one.
Oh.
That should be easy, guys.
From 16 till 13.
50%.
Yeah. The percent will be, you see, isn't that half of the curve? 22 is the middle, it's the center. This is half of the curve, right? This is 50%. And if I ask you, what percent of the scores are above 22 will be the other 50%.
To put 49.85, or would you accept 50%?
Oh, no, 150%.
Okay.
Because remember, this curve doesn't end here. It has a tail that extends forever to cover those 0.3%, but we don't count it. We stop here, but there is more. The more is the 0.3% that we didn't count. So actually, if you guys think that the curve ended here, no, actually the computer shows it ends, but that doesn't end. The tail extends indefinitely forever this way to cover the 0.3%. I don't want you guys to, dig deeper into this other than what I just want you to know. I want you to memorize the 68, 95, and 99.7% rule for now. So I ask you a question. What percent of the students score between 19 and 25? You say 68%, which is correct. Now, what about if he tell you there were 500 students? How many of those students score between 19 and 25? How would you figure this out? I'm gonna get the calculator ready. So you agree the percentage is 68%?
Yeah. You go 500 times 0.68.
Exactly. So you guys, you have the 0.68, which is, and then how many students do I have times the 500? There you go, 340 students. So if you have the total number of students, you can figure this out if you know the rule. Now, the empirical rule, guys, this rule, the 68, 95, 99.7% work only in a symmetric distribution. If the distribution is not symmetric, this rule is void. We cannot use this rule. Okay. I want to do this example, just a part of it, and then I want to go to something else. The scores of all high school seniors at Pope taking the verbal section of the Scholastic Aptitude Test, it's a SAT test, in a particular year had a mean of 490 and a standard deviation of 100. So the mean, guys, is 490 and the standard deviation is 100. The distribution of the scores is bell-shaped, so he tells us it's symmetric. Draw the normal bell curve. Let me draw the normal bell curve for you guys. I'm gonna do it right here. Just do this. Put the mean in the center, which is 490. And can you guys help me with the standard deviation? We need a 3 to the right and 3 to the left. So with the 100, you guys agree 590, 690, 790, 390, 290, and then 190. I don't think there's a score of, yeah, there could be just on the math by itself. Yeah, there could be 190. Okay. What percentage of the scores are between 390 and 590, guys? That should be easy. Ask yourself, is this 1 standard deviation, 2 standard deviation, or 3 standard deviations? What percentage of the scores are between 390 and 590?
That's 68 because it's 1.
68% because it is 1 standard deviation. It goes 1 way to the left, 1 way to the right. So that's the answer, 68%. One student scored 795 on this test. How did these students do compared to the rest of the scores? 795 is right here, guys.
Outstanding.
Not just outstanding. What do we consider this score? It's an extreme value, an outlier. So would you guys agree that he did better than everybody?
Yes.
He did. Because we said we can't go beyond the 3 standard deviation usually. And this guy went beyond the 3 standard deviation. He's at 795.
So he's an exception.
An exception, exactly. Exactly. It's an exceptional score. And you know, 795 is a very good score because 800 is the maximum score that you can get. Not many students get a perfect score each year. I mean, you hear of a few students each year who get a perfect score on the set. So exceptional. A rather exclusive university only admits students who were among the highest 16% of the scores on this test. What score would guarantee admission to the university? So if you are in the top 16%, you will be admitted to the university. Can you tell me what minimum score should you get in order to be in the top 16%? Remember, guys, highest 16% should be on this side.
So it's from 690 until 790, or no?
You mean 690 and up?
Yes,
Even
690.
we don't stop at 690, but it's not 690. It's a different number. Okay, you guys agree with me that this is a 34%? That's a 34% because together are what? 68%. So, and where is the location of this? At what percent is the 490 located? It's in the middle. And what's the middle? What percent would the middle be?
50.
50%. So if you guys add 50% and add 34%, that would give you what? What's 50 plus 34?
84.
84. What's left from 100%?
16.
16. That's what we want. We want this, guys. So what does this start at? What score? 590. So it's 590 and up, not 690 and up, because the 16% starts right there. This is the 16%. This is the beginning of the 16%, and this is the end. So that will be 590 or more. Okay, last one. The senior class at POP has 450 students and offer 500 scholarship to everyone that gets above 690. What percent of the students will get this scholarship? Above 690 right here, guys.
That'd be 8%.
Oh, but no, that doesn't go into half. You're thinking that the 690 is halfway between these two. I see your point, but remember the curve is not like, you know, a rectangle to split it into halves. You know, it is fat here, but thin here. So this has a lot more than that part. You can't just do it this way. I'm gonna sketch the curve on another piece of paper so you can see it clearly and tell me what percent of the students are gonna get the scholarship. So I'll do it here. Watch, guys. What was the mean for 90? Okay, watch. 590, 690, 790. And we said above 690. So right here. Those students, guys, from here and up will get scholarship. What percent is this? This is 390, 290, 190. Can someone figure out the percent?
It's like either 13% or 16%.
It's going to be a lot less than that. This is 34%.
Around 10 or 8, something like that.
Any other ideas? How much is this, guys? Tell me what about this. Can someone tell me this? This is 2 standard deviation to the right from the mean. Who can tell me what this one is? What percent is this? What did we say 2 standard deviation? What's the percent for 2 standard deviation? 95%. If I want to take half of this, only 2 standard deviation to the right, what do I do with the 95%?
Cut it in half, so it's 47.5.
Very good, 47.5%. Guys, this is 47.5%. What's left for this? You remember, a half is 50%. So what's left for 690 and up?
2.5%.
Yes. The answer is 2.5%. Anyway, guys, I just showed you how to do this. This is something we're gonna revisit in chapter 5, and we don't need to memorize the 68, 95, 99.7% later, because we'll be able to find all those numbers. But all I want you from this to understand, 68% means 68% of the data fall within 1 standard deviation of the mean, 95% of the data fall within 2 standard deviation of the mean, and not 100%, 99.7% of the data fall within 3 standard deviation of the mean. And I like you to understand the word within to mean above and below. So if I ask you guys, I'm meeting with you today at noon, and just come to my office within 5 minutes of our appointment. It's not like I'm asking you to come only early 5 minutes, but I'm saying it's okay also to come late 5 minutes. That's what within means. All right. And the last part, which is actually an easy part, measures of position. Okay. Let's introduce, guys, the measures of position and explain to you what they mean. What's your position on the number line or on a scale? We're going to talk about this. And I'm going to start with this example, and then I'll go back and explain this. Okay, you have a data set, guys. First of all, when you talk about the median, you have to arrange the data set in order. So anytime you talk about a position, location of a number, you have to put the numbers in ascending order from smallest to largest. So I have this data set, and I'm asking you to find the median for me. So you go and arrange the numbers in order. How many? I have 15 workers. Do you guys know where the median is located without trying to find it? Can you tell me where the location of the median is going to be?
On the right.
Yeah, but which position? You have first, second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12. Where is it going to be located? What did I say to do when you have an odd number of values? You add 1 to it. So what's 15 plus 1?
16.
Divided by
16.
2. 8. Count to
8.
8. 1, 2, 3, 4, 5, 6, 7, 8. This is your median, guys. Here is another way to do it, guys. Cross 1 off here, 1 off there. 1, 1, 1, 1, 1, 1, 1, 1, 1 here, 1 there, 1 here, 1 there. This is the leftover. That's the median. So the median is 20. Now let me tell you what the first quartile, which the calculator displayed, and I didn't say anything about it because we haven't done it yet. The first quartile, it's called the quarter one. It's the middle of the first half of the data set. Since this is the median, guys, this is your first half. It's below the median. And the second half, guys, is right above the median. So can you guys ignore, just everything else and tell me what would be the median of this data set now? I have 5, 10, 10, 10, 10, 12, 15.
10.
10, exactly. This is called first quartile. It's called the Q1, and it is a 10.
Sir, I have a question.
Yes.
So in the first quartile, why did you pick the left side?
Oh, the first quartile is the left side.
Oh, and that third.
And the third quartile will be on the right side. Yeah, the first
Okay.
quartile is the first quarter. You
I
start
think
from
said
the
this
left.
before,
Yeah.
but I forgot. Sorry.
No problem. Third quartile, guys. Hide the first half and figure it out. I need a median as well. So the median is covered. And what would be the median of the second half?
30.
Oh, yeah.
Or
Oh, sorry, I covered the wrong value here. So that's it right here.
30.
Yep, it is 30. I have 7 values. Add 1, that will be 8. Divide by 2, 4. Count 4. 1, 2, 3, 4. It's 30. The good news is your calculator can do all of this anyway, but sometimes it's faster to do it by hand if you have a small data set rather than entering the data into the calculator. Minimum value, guys, is the smallest value in the data set, which is 5. And maximum value is the largest data set, the data value, which is 60. Those 5 numbers, guys, the median, the first quartile, the third quartile, the minimum, the maximum, are called the 5-number summary. So if you are doing homework and you are asked to find a 5-number summary, you need to find those numbers. Median, and the median, guys, it's called the Q2. So Q2 is the median, Q1 is the first quartile, Q3 is the third quartile, the minimum is 5, and the maximum is 6. Let's see this example, another example. I have an even number of observation. I have 1, 2, 3, 4, 20 New Yorks. So how do you find, the median? If you have a 20, guys, divided by 2, it will be 10. So your median should be between the 10th and 11th position. Watch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's right here. So what do you think the value is going to be for the median, guys? It's not the 20. It's not 25. We have to make a compromise here. So it will be what? 20 plus 25 divided by what? 2. Which is 22.5. Now let's find the first quartile. The first quartile, okay, this is the median right here. And this is the first half. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So your median, guys, is going to be between the 5th and the 6th. 1, 2, 3, 4, 5, 6. Well, it's the same. It's between 15 and 15, so it must be 15. Here you go. Let's go to the third quartile. Take the second half and ignore this half, guys. You can ignore this half. It's between the 5th and the 6th again. 1, 2, 3, 4, 5, 6. Between 40 and 45, right here. So it will be 40 plus 45 divided by 2, which is 42.5. And the minimum, guys, what would be the minimum here? The smallest value, 5. And what's the maximum?
85.
85. All right. Using the calculator. You guys don't have to worry about even arranging the numbers in order. So I'm gonna show you how to use the calculator to find those 5 numbers. Add it. Okay, L1. I'm just gonna put any numbers in there. I think that's enough. I got 15 values. We're gonna ask the calculator to find the mean, not the 5 number summary for us. So watch, guys. You don't need to arrange the data in order. All you need to make sure that you enter the right data, because sometimes students make mistake. Instead of putting 9 here, they put 90 by mistake. Just be careful. There's no way for me to verify, you know, what you did on the calculator. So stat, edit, stat calc, and just click enter. And L1 confirm, so scroll down. And here you go. Minimum 2, Q1 7, Q2 median 9, Q3 15, maximum 19. That's it. That's how you use the calculator. Any questions, guys, so far? We're good? We understand the 5 number summary? Okay. I'm assuming that your silence is a consent that we do understand. Let me see, I have a chat here if any questions. Okay, good. All right. Now you're gonna learn, guys, how to find if a data set has an outlier or not. So I have this data set, and we're gonna check if this data set has an outlier. If there is an outlier, guys, which number would you suspect to be an outlier in this data set?
85.
85, okay. I knew that you were gonna say 85. But you cannot just say, because I feel it is an outlier, it is an outlier. Probably it's not. It's not too far from 65. Maybe another students would say 5 is an outlier, but well, 5 is close to 10 also, and 10 is there. So you're ready, guys? We're gonna go through the process of checking for outliers. Unfortunately, the calculator doesn't do this for you, so you just have to learn it from me, and I'm gonna show you. It's very easy process. Watch. First of all, we find what we call the interquartile range, which is Q3 minus Q1. And it's called IQR. And by definition, guys, this is a Q3 minus Q1. We already did Q3, we already did Q1, so we just put it there. This is a Q3, guys. And this is a Q2, Q1. So it will be 42.5 minus 15, which is what, guys, 27.5. I'm gonna go slow with this step by step. This is step number 1. The first step is to find IQR. If you are doing homework, guys, and the author asks you to find IQR, it is Q3 minus Q1. Step 2, multiply IQR by 1.5. Always 1.5. That's a fixed number, guys. Okay, can a student multiply this for me, please?
$41.25.
41.25. Thank you. Step 3, which is the last step before I tell you what if there are outliers. Take a Q1 and subtract this number, and take a Q3 and add this number. So what's a Q1, guys? We did find it, which is 15 minus 41. Can a student do this for us? And Q3, guys, it was 42.5 plus 41.25. What is 15 minus 41.25? It's what? Negative 26.25. And what is this one? 83.75. Any guesses, guys, how I'm gonna tell you if there are I'm ready to tell you if there are outliers or not.
So anything below negative 26.25 or above 83.75 should be the outlier.
You nailed it. You nailed it. Anything that is between these two numbers are not outliers. Anything that's beyond those two numbers is an outlier. So if you have any number below negative 26, which we don't, they are all positive. But if you have any numbers above 83.75, is considered an outlier. It almost passed, but it didn't. So do you guys see any numbers that are above 83.75?
85.
85. You see, it's a close call. Some of you thought it was an outlier, but maybe other students wouldn't think it was. And it was very close. We almost missed, but it is an outlier. It doesn't belong there. So this is the process of finding outliers. We'll get a chance to do another exercise later, but the steps, guys. First of all, you find the IQR, Q3 minus Q1. Multiplied by 1.5. Whatever the number is, let it be. Then you take a Q1 and subtract the number from step 2, and then take a Q3 and add the number from step 2. And any number that falls between the two numbers is not an outlier. Any number that goes below the first one and above the second one is an outlier. And that's how we determine that 85 is an outlier. But I'll give you some situation, guys, where you really don't need to do any work to check on a number if it is an outlier. I mean, if I would do it, even I wouldn't do any work if I said I have a set like this. Do you guys really need to do any work to make sure that 175 is an outlier?
Oh, that's obvious.
That's obvious.
No.
If it is obvious, you can take your chance and say this is an outlier. But if you guys put 8 here, be honest with you, I don't know. I don't know if 8 is an outlier or not. And you know what, guys? Let's do it. I'm gonna do this. So first of all, guys, you have to help me arrange the data in order. So we have 1, 1, 2, 2, 2, 3, 3, 4, and then 8. Okay, we need the Q1, Q2, so we need the 5 number summary. So how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 add 1, 10, my median is the 5th. This is median, that's a Q2. Can you guys tell me what Q1 is? It's right here. So who's going 1.5? Very good. Who can tell me what Q3 is?
3.5.
3.5. And this, okay, I'm ready now to find if 8 is an outlier. So I do the IQR, which is Q3 minus Q1, guys, which is 3.5 minus 1.5, which is 2. Then I multiplied step 1. Step 2, I multiply by 1.5. That's a 3. Number 3, I'll take a Q1 and subtract 3, and I'll take a Q3 and add 3. Q1, guys, is 1.5 minus 3, which is a negative number. Okay. Q3, 3.5 plus 3, 6.5. Are there any outliers, guys?
Yeah.
8 is an outlier. You can see because 8 is more than 6.5. Anything confined between 6.5 and negative 0.5 is not an outlier. Now, honestly speaking, guys, if this was a multiple choice and you wanted to take your chance, probably some of you would not have said that 8 is an outlier because it looks close to 4. And maybe some of you would have said that it is an outlier. So if it is a close call, guys, don't take a chance because you could be right and you could be wrong. But if this was 80, guys, I wouldn't even want you to do the work. Just say 80 is an outlier because it's way, way far removed, you know, just from the data set. So I hope that this makes sense to you. Another thing I want to talk to you about is the percentile, and I think you hear about this, guys. So let me tell you what a percentile is. For example, if I report to you after the first test, and I tell one of my students that you scored in the 95th percentile, what does this mean? Does anyone know what a percentile means? So we learned about the quartile, quarter 1, quarter 2, quarter 3. What is a percentile? So
Like in the top scores, or
what is it?
it's in the top scores.
It could be, but it means something different. It means that, let's say I tell you, is this Ghassan?
Yes.
Let's say, Ghassan, I tell you, you scored in the 95th percentile. What I'm trying to tell you, you did better than 95% of the students. That's what
Like
it means.
exceptions or something.
So it's you did better than 95% of the students. And that means 5% of the students did what?
Less
Better than you. So you
Oh,
did better
five-
than 95% of the students, but there were 5% of students. Now, it doesn't mean that the person got an A, because it could be that the person got a C and everybody else got a D. So but it could also be that students got the highest score, but it doesn't mean that it is. So you cannot tell whether the score is good, but you can tell, you can relate your performance to the rest of the class with the percentile.
Oh,
So
okay.
if I tell you you scored in the 80th percentile, that means you did better than 80% of the students. But it also means that 20% of the students did better than you. Do you guys know where I come up with the 20%? Because 100% minus 80 is 20%. So this is what percentile is. And on standardized tests, guys, like the ACT, the SAT, and some other, just standardized tests, they use percentile to determine scores, how students perform, just relating to each other. So they use this fact. Your quartile 1 is in the 25th percentile. And let me tell you why. Here's your data set. Here's your median. Your median is in the middle, so it's in the 50th percentile. And we can write it Q2. And now since we're using percentile, they refer to the median as P50. P50, guys, refer to percentile 50%. Now, Q1 is the first quarter. It's called the Q1, and they use P25 because it's right at 25%. Because this is 25% of the data, guys. This is another 25% of the data. And now I'm going to go another 25% to Q3, which is, they call it a P75. P75 means 75th percentile. 50th percentile, 25th percentile. That's a Q1, that's a Q2, and that's a Q3. We will be using the quartile more than the percentile, but it's good, guys, to know what a percentile mean. And be honest with you, there are some people misinterpret the percentile. Like a student will report, to their parents and show them, just transcript showing that the students got in the 90th percentile. Well, some parents interpret this as an A or something like that, but it only means that the students did better than 90% of the other students in his class or her class. But it also means that 10% of the students did better than that particular student. So that's what I want you to understand about percentile, guys. All right, the last part, and then we're going to do some fun activities after that. Any questions, guys, about percentiles? All right. Let's talk about okay, before we do this, we're gonna do this activity together. I'm just gonna make sure that you guys know how to use the calculator. So I'm gonna pause for a few minutes and I'm gonna have you enter RIDE A information in list 1 and RIDE B information in list 2, and then we'll read the question together and show you what we're gonna do with this question. So if you have your calculator handy, guys, please get it ready and follow my directions and how to use it in entering the data from RIDE A and RIDE B. Okay, here's the question. So we enter the data sets into the calculator, and the question states whether the data sets in A and B are sample or population, find the range, variance, and standard deviation of each set. Use the standard deviation to compare the variability between the data sets. First question, guys. Do the data RIDE A and RIDE B wait times represent a sample or a population?
I think it's a sample.
You should confirm that, because wait times, there are more than 12 people who ride, just on this. So it is a sample. If you have a ride, just like in Disney, thousands and thousands and thousands of people use it. We only have information about 12 wait times on each ride. So definitely this is a sample, guys. It can't be the population. And the hint why I asked this question, because later when you find the standard deviation, you're not going to look for sigma, you're going to look for S. So a sample. Okay, we want the range. We're going to let the calculator do the rest now. Watch. You go to stat, calc, one variable statistic. Okay. If you press enter right now, guys, it's going to process L1. And yes, we need to process RIDE A information. So let's do that. Okay. He doesn't want the mean. He says, I want the standard deviation and the range. The range, guys, is the difference between the maximum and the minimum. Okay, can a student tell me what the standard deviation is?
14.5.
Yes. It's not the sigma, it's S, because it's a sample. Remember, S refers to a sample standard deviation. So RIDE A, S equals 14.51. I'm going to make 2 digits. And now I need the range. Let's read the minimum and the maximum, guys. Scroll down.
11 to 6.
Minimum is 11 and maximum is 60. So 60 minus 11. Right B. Okay, let me go to the calculator. I'm gonna quit. Maybe guys, you can give me a hint what to do now. I'm gonna go to stat, calc, one variable statistic. Guess what, guys? If I press enter, what's gonna happen? What do you think is gonna happen if I press enter? It's gonna take me back to L1. It's not gonna do L2. By default, it will do L1, the calculator. So now you have to tell the calculator, go to write B, and it's in L2. Any guesses on how to go about doing this?
You hit second and then number 2.
Yes, you put second and number 2, L2. And if you guys, you have this calculator, watch, this is what you do. You go to stat, calc, one variable statistic, and you change this one to second and then number 2. Like this, as simple as that. If you don't do that, guys, you're not going to be able to find the standard deviation of L2. If you guys get confused, you don't know what to do, you just delete the data in L1 and put L2 data in there and just do it again using L1. But you can do them both at the same time. That's what I'm trying to show you here. Enter. And here you go. I need S, which is 6.50. I'll write it down. And let's do the range. I think it's going to be a smaller range probably. Minimum is 31 and maximum is 50. 19. Use the standard deviation to compare the variability. So which ride, let's say, which ride would you consider, guys, if you were consistent about, you know, just weight, if you were concerned about, you know, wait time, which one would you consider?
B.
B, definitely. Why? Because it has a smaller standard deviation. So ride B has less variability than ride A because it has a lower standard deviation. And you guys, you could have even used the range. Look at the range here, 19 minutes and here 49 minutes. If those rides are very much, let's say, the same, I would prefer, you know, just to go and wait in line for ride B, because my chance in the worst scenario that I would have to wait 19 minutes more than the person who waited the least. But if you go to ride A, your chance, if you're in the worst scenario, you have to wait 49 minutes more than the one who waited the least. So that's why ride B is better. So more consistency, guys, when you have a smaller standard deviation, remember that. So that's how you use standard deviations. Okay, that's 19 here. And we'll come to the last part of this, which is z-scores. So just, I'm gonna explain this to you guys, and that would be it. And the z-score is extremely important to learn because that's gonna follow us throughout the semester. So I'm gonna just try to explain it right here. This is the mean, let's say make it 50, and let's say the standard deviation is 10. So if you guys do 3 tick marks, can you help me fill in the numbers? What would that be?
60.
60, 70, 80, and what would that be on this side?
40.
30,
20.
20. Okay. Let me ask you a few questions here. Take number 70. How far apart 70 is from the mean? What's the distance between 50 and 70? How far away are they apart?
20.
20, because the difference between 50 and 70 is 20. So 70 is 20 points away from the mean, which is 50. So 20 points. Can you guys tell me 20 points is how many standard deviation is 20 points? Each standard deviation is worth 10. So how many standard deviation this is? Let's see. 1 or 2? Each standard deviation is worth 10. Yes, it's 2 standard deviation. Okay. So would you guys agree with me if I put 70 is 2 standard deviations above the mean? Let's take 40. What's the distance between 40 and the mean, which is 50? How far apart?
10.
40 is 10 points away from the mean. Is 10 points, how many standard deviation is 10 points, guys?
1.
1 standard deviation. Each standard deviation is worth 10 points, $10. So 40 is 1 standard deviation below the mean. I'm coming to the definition in a second about the z-score. I want to do one more example now. Now I want to take 55. How far is 55 from the mean?
5.
55 is 5 points above the mean. 1 standard deviation is worth 10. 5 points will do. Do you think how many standard deviation is this? Each standard deviation is worth 10 points. So 5 points will be what comparing to standard deviations?
Half.
Half, because the standard deviation is 10. 5 points is half of the standard deviation. Is a half a standard deviation above the mean. Last one, I'm going to take the point 20. What's the distance between 20 and the mean? It's all about the mean, guys. We compare everything to the mean. We need to know what's happening around the center of the data set. So the mean is very, very important. You're going to notice all the statistics is about the mean, the average. So 20 is how far apart from the mean? It's 30 points. You guys agree it is 30 points? From 20 to 50, 30 points. How many standard deviation is that? Each standard deviation is worth 10. 3. So 20 is 3 standard deviations below the mean. When we compare numbers on the number lines to the mean using a standard deviation, we are talking about what we call a z-score, a standardized z-score. So the z-score, guys, is how many standard deviation does a number deviate from the mean. So you told me 70 is 2 standard deviation above the mean. The z-score for 70, they call it z, will be a 2. And I'm going to give you a formula on how to find the z-score. You're going to see how easy it is. You said 40 is 10 points away from the mean. You say 40 is 1 standard deviation below the mean. Can you guess what the z-score, since it's below the mean, not above the mean? It's 1, but it can't be a plus 1 because the plus goes above the mean and the minus goes below the mean. So it's -1. Let's take 55. 55 is half standard deviation above the mean. So the z-score, guys, would be a half. So for above, it is positive, and for below, it is negative. 20. 20 is 3 standard deviations below the mean, so z will be -3. So the z-score counts how many standard deviation the number is above or below the mean. If the number is above the mean, it will be positive, and the z-score will be negative if the number is below the mean. What about if I take the mean itself, 50? How far apart is 50 from the mean itself?
0,
0. So what's the z-score for the mean?
0.
0. If z equals 0, then the value is the average itself, is the mean itself. And here's the formula, guys, that we can use to find the z-score. Watch. Z-score, it's already on the notes. I'm going to put it there, equals value minus mean divided by standard deviation. Okay, let's see if this formula really a valid formula. I want to check if it works. Okay, let's take the value 70. We decided that z equals 2. Let's see if this is going to work. So the value is 70. I'm going to put 70 in here. Minus the mean, which is 50, divided by the standard deviation, which was 10. What's 70 minus 50, guys? Is 20. And divide by 10, that will give you a 2. You want to do the half. I want to show you the 55 is going to lead to a half. Value is 55. So let's see what the z-score is. 55, watch, guys, minus 50 divided by 10. A 55 minus 50 is 5 divided by 10. That will give you a half. Let's see why we got a negative number here. The z equals -3 for the value 20. Watch. Value equals 20. Z will be, which value? 20. Minus 50 divided by 10. What's 20 minus 50, guys?
-30.
-30. It's not 30. It's -30. And divided by 10, it's going to give you a -3. So z-scores can be positive if the values are above the mean, can be negative if the values are below the mean. So let me make this statement, guys. If I come to a students after the first test, and I tell the students that your z-score on the test was 2.5, should the students be excited about the grade?
Yes.
Very excited. Your 2.5 standard deviations above the mean. Your score is going to be very high. What about if I tell the students your z-score on the test was 0? What can the students interpret from this?
That they were at the mean.
At the average. So if the average of the class was 75%, this student got exactly 75%. But if I tell a student your z-score was -1 on the test, should the students be concerned?
Yes.
The students should be concerned because a z-score of below 0 means you are below the mean. You should be concerned. And if I tell you your z-score is -2, you should be very, very concerned because you are 2 standard deviations below the mean. When you are 2 standard deviation and above below the mean, that means your score is very, very low. So this is how we interpret z-scores. Actually, there is an instructor of statistics, guys, for your information. On his syllabus, he explains, the grading policy using z-scores to students. They don't get it at the very beginning, but he goes back after he introduced z-score and explained this policy. So let me go back here and just put the definition of a z-score. We'll be able to wrap this up and do our activity in a few minutes. So z-score equals value minus mean divided by the standard deviation. Or you can write it like this. Z equals X minus mean divided by sigma. X is the value, guys. Mean is the average, the mean. And sigma is the standard deviation. If you have a population. And you're gonna see this formula as well, guys, which is exactly the same. But if you have data that comes from a sample. This is the value. This is the mean. And this is the standard deviation. You can memorize it any way you like, as long as you put the value first, minus the mean divided by the standard deviation. Here is an example. The mean is 75, the standard deviation is 6, and X equals 83. I want you to find the Z-score. So you do this, guys. You put 83 first, you minus the mean, and divide by 6. And do not do this on the calculator, guys. I'm gonna do this and show you what some students have been doing, giving me wrong answers. Watch. Students wanted to use the calculator, so they do that. That's wrong. Look at the answer. The Z-score is too big, you know, of a Z-score. So do you know what went wrong? Because of the order of operations, you need to do 83 minus 75 first, but what the calculator did here, it did division first. It divides 75 by 6 because I didn't put parentheses. So to be on the safe side, if I were you guys, I'll do this. And then divide by 6, which is 1.33. Okay. So this is the Z-score. If your Z-score is between -2 and 2, it is a usual normal Z-score. It can happen most of the time, but your value will be unusual if your Z-score above 2 or your Z-score below -2. So if you get a Z-score more than 2 standard deviation and below 2 standard deviation, that means your Z-score is unusual. I told you guys, according to the rule, 99.7% of the data falls within 3 standard deviation of the mean. So usually we cannot go beyond a Z-score of 3. So a data value is very unusual if your Z-score is more than 3 or your Z-score is less than, can someone guess what I'm gonna put there?
-3.
Yeah. And I'm gonna add one more thing here. A data value is usual if Z is between -2 and 2. Any score that is between -2 and 2, guys, is usual, can happen. But any score that starts to go beyond 2 and below -2 is usually unusual because you're beyond 2 standard deviation of the mean. That should not happen. We're gonna do this example. That's the last example, and we're gonna open the activity in Socrative. So let's do another example on Z-scores to give you a better feel of what Z-scores are used. So how would you compare, you know, just whether a student did better on the SAT or ACT? They use different scoring rubrics, you know. SAT is out of 1600 and ACT is out of 36. So how can you tell whether the students did better on the SAT and ACT? We're gonna do this. So Eleanor scores 680 on the SAT mathematics test. The distribution of the SAT scores is symmetric and single peaked, means bell-shaped, with the mean of 500 and a standard deviation of 100. So that's the mean, and that's a standard deviation. Gerald takes the American College Testing, ACT, and scored 27. ACT scores also are symmetric with the mean of 18 and a standard deviation of 6. He wants us to change each score to a z-score. So we're gonna do the SAT score for Eleanor and the ACT score for Gerald. So SAT. What was the X value? 680. What was the mean for the SAT? It was 500, and the standard deviation was 100. Okay, can you guys help me change this one to a z-score? I'm gonna call it ZSAT. It will be what? X value is 680 minus 500. So can you guys tell me which students did better relative, you know, to the test SAT or ACT just by looking at 680 or 27? Which one do you think? Actually, you can't, because it's just like comparing apples with oranges. They're two different tests, two different, you know, scoring rubrics. So you cannot tell. But if we change to z-scores, we're going to be able to tell. You will see. So I'm going to change the first score to a z. 680 minus 500 divided by 100, which is 1.8. And let's go to Gerald now. What was the score? He got 27. What's the mean? The mean was 18, and the standard deviation was 6. So let's see what the ZACT was. 27 first, you put the value first, look at the formula, value minus the mean, 18, divided by 6. 9 divided by 6, which is 0.1. So can you guys tell which students performed better relative to the test? Was it Eleanor or Gerald?
Eleanor.
Can you guys agree with her? Because she had a higher z-score. So because she had a higher z-score, she did better relatively, not just to the test. So did better because her z-score was higher. So you guys, if I tell you on the first test, one of you got a z-score of 1.2 and another student got a z-score of 1.8, definitely guys, right away, you can make a conclusion that the students with a 1.8 z-score did better than the 1.2. That's for sure. And always a positive z-score is better than a negative z-score, definitely. So this is for z-scores, and that concludes everything I need to talk about in chapter 2. What I'm gonna do now, guys, I'm gonna open that activity that I emailed to you. I'm gonna break you out into a room for 10 minutes and then have you come back, and then we're gonna go over the answers through Socrates. So I will break you out into groups. And open, all right, just one sec. Let me stop, pause recording here.